Welcome to Prospective Doctors MCAT Podcast, brought to you by Med School Coach. Each week, Sam breaks down the highest yield MCAT topics so you can score as high as possible on test day.
Hello and welcome to Prospective Doctors MCAT Basics with your host Sam Smith. The goal of this podcast is to cover the highest yield topics on the MCAT and provide you with some sort of insight into the questions that the MCAT really likes to ask. In addition, I'll tie in some of the testing strategies that I and other students have used on the MCAT. This podcast will cover the main functional groups to know for the MCAT. What I'm going to do is I'm going to introduce the different functional groups to know. Then I'll talk about their physical and chemical properties, their relevance in biological reactions, and then their reactivity. And then lastly, I will mention how the MCAT likes to ask questions regarding these functional groups. This material shows up in 2 out of the 4 MCAT sections. That's going to be the Chem Phys section and the Biochem section. And all in all, understanding functional groups and their reactivities, their physical properties, their chemical properties, all that is very important for the MCAT. You will see problems on the MCAT regarding functional groups. So before I get started talking about the actual functional groups themselves, I want to talk about what physical properties are, what chemical properties are, and what intensive and extensive properties of some material are. These are both terms I'm going to use throughout the podcast, so it's important that you know what these mean so that when I say it, you're not like, oh, what does that mean? Physical properties of material are those that can be observed without changing the identity of the substance. So examples are boiling point, solubility, and stuff like how strong is this compound? How much does it bench? That's a good example. Chemical properties, on the other hand, are properties that you need to change the identity of this substance in order to measure that property. So for instance, combustibility. So when you burn something, it obviously changes. You burn a hydrocarbon, you turn that hydrocarbon into carbon dioxide in water, right? Anytime you combust something, it reacts with oxygen in the atmosphere to then produce carbon dioxide and water. So that's just an example of a chemical property, right? You have to change the identity of that substance in order to observe the property. So that's the difference between physical and chemical properties. What about intensive and extensive properties? Intensive properties are physical properties that will be the same regardless of the amount of matter that you have. So for instance, density is an intensive property, right? It's a mass per volume. It doesn't matter how much mass you have, the density is always going to be the same because it's mass per volume. Same with conductivity. It doesn't matter how much you have of a certain metal, it's going to have the same conductivity. And then same with specific heat. And so a specific heat is the amount of heat required to raise a certain amount of some material by 1 degree Celsius. And again, it gets at a certain amount. That's the most important part about an intensive property. On the other hand, an extensive property is a physical property that will change if the amount of matter changes. So, mass, volume, just general heat capacity are all examples of an extensive property. All right, so let's get into the different functional groups. The first functional group I'm going to talk about is an alcohol or a hydroxyl group. So this is simply an oxygen attached to a hydrogen, an OH, and that's attached to something else. So that's an alcohol group. And the names of different alcohols usually end in -ol. So for instance, we have methanol, which is also called methyl alcohol, which is just one methyl group attached to a hydroxyl group or an alcohol group. And then you have ethyl alcohol or ethanol, which is 2 carbons attached to an alcohol group. Then, as we continue to add on more and more of these carbons, you go to propyl alcohol, when you have 3, then butyl, and so on. So again, important to recognize there that when you have an ending in ol, that's an alcohol, or you might have something like ethyl alcohol, which is a different naming system, but means the same thing. And just a quick aside, in organic chemistry, you learn all of the different IUPAC naming systems, and propanol can be prop 1-ol or prop 2-ol, whatever that is. I wouldn't really worry too much about the IUPAC naming system. First of all, you just need to be able to recognize names, not even produce them out. So I'm sure you'd be able to recognize prop-2-ol and say, okay, this is a propanol, but there's the OHs at the second carbon, whatever. Be able to recognize. More important, though, is the common naming system. So be able to really kind of recognize these common names more than the IUPAC naming system. That's kind of important for the MCAT. Alcohols can be classified into three main groups. There's primary alcohols, secondary alcohols, and then tertiary alcohols. Primary alcohols are alcohols in which the carbon attached to the alcohol group is attached to 2 hydrogen in 1 R group. So that's primary alcohol. A secondary alcohol is an alcohol in which the carbon attached to the alcohol is also connected to 1 hydrogen in 2 R groups. And then you have a tertiary alcohol, and that is an alcohol in which the carbon that's attached to the alcohol is also connected to 3 R groups. I like to think of it, primary is smaller, secondary you're getting a little bit bigger with that 2 R groups, then tertiary is this huge massive molecule because it's got these 3 R groups attached to this alcoholic carbon. And each of these different types of alcohol have different physical properties, right? Tertiary has different properties than secondary, which has different properties than a tertiary. So let's get into that and let's talk about why these alcohols are all different. So again, physical properties are properties of substances in which you don't have to change the identity of the substance in order to observe. So in terms of alcohols, one thing that influences the physical properties are the fact that alcohols can hydrogen bond, right? So what are the molecules again that can hydrogen bond? It's easy. You just remember FON. FON can hydrogen bond. FON is the one, right? Fluorine, oxygen, and nitrogen. Those are the 3 elements that when bonded to hydrogen can hydrogen bond. And since alcohols can hydrogen bond, they have relatively high boiling points, right? You have to put in a lot of energy in order to break those hydrogen bonds that hold all of these alcohol molecules tight together. And again, hydrogen bonds are an intermolecular force. In addition to a high boiling point, these hydrogen bonds enable alcohols to be soluble in water. Basically what happens is the alcohols hydrogen bond with the waters, which hydrogen bond with the alcohols, and everything just kind of gets mixed up. You don't have these phases that become separate. You just get a nice mixing of these 2 liquids. And so you can say that they are soluble in one another or they are miscible. And this principle kind of brings me back to high school. I had a friend who would take his parents' alcohol and he'd drink some of theirs, and then he would pour water back in. And, they mix together, and you can't tell that part of this alcohol is now water, except for the fact that his parents would actually take this and they go put it in the freezer. And this mixing actually caused the alcohol to have a lower freezing point. And this bottle of alcohol that used to not freeze actually now freezes because my friend from high school mixed water with it. And he got in trouble. And I think his parents locked up the liquor or whatever into a cabinet after that. But I just remember that. And so you can remember that these mix together well, because you can mix water with alcohol, make mixed drinks, you don't get sediment or you don't get partitioning of 2 different layers when you mix alcohol and water. And one important trend you'll see with solubility is that the addition of hydrocarbons decreases solubility. So for instance, you look at the solubility of ethanol, you compare that to the solubility of something like propanol, and you see that the solubility actually decreases. So the addition of further methyl groups actually decreases solubility. And as with a lot of other functional groups, the limit of solubility is around 5 or 6 carbons. So by the time you go from ethanol to methanol to propanol to butanol, all the way up to 5 carbon pentanol, by that point you actually have an alcohol that is no longer soluble within water, or at least very limitedly soluble. So just keep that in mind. And this is a trend you'll continue to see as I keep covering these different functional groups. So for instance, you can say that ethanol is completely miscible within water. That is to say that you mix 1,000,000 grams of ethanol with water, it's all soluble, everything mixes well. Well, for pentanol, on the other hand, only 2.7 grams of pentanol dissolve into 100 grams of water. So you only have basically 2.7% by volume pentanol is soluble within water. And so as I mentioned previously, primary alcohols, secondary alcohols, and tertiary alcohols all have different boiling points. So for instance, primary alcohols have the highest boiling point, secondary alcohols have a lower boiling point, and then tertiary alcohols have the lowest boiling point of all. And you might be thinking, okay, why is this? Essentially, this is because as you add R groups onto these alcohols, you get these bulkier and bulkier molecules. And so it is actually harder for these molecules to hydrogen bond because they have to get in at the right angles in order to hydrogen bond, to get close enough to hydrogen bond at least. And because of these bulky R groups, they're not able to do that as well. So you can kind of think of this as the following example. So you have a jar of cookies and you're trying to fend off people from taking your cookies because cookies are good, right? You want your cookies. Now, if you have really teeny, short, stubby arms, let's say like a Tyrannosaurus Rex, you're not going to be able to fend off shit. People are just going to be taking your cookies left and right, and you're not going to be able to do anything about it. Well, that's like a primary alcohol, right? It's got these short little stubby arms, and therefore things can get in easily and just hydrogen bond to it. Whereas you go to the case of the tertiary alcohol, it's got these long arms that are big and wily and just slapping the shit out of people, and people can't get in there to take a cookie, right? You keep all your cookies to yourself. You might start to get heavier after a while, but the point here is that this is like the case of a tertiary alcohol where you have these long, big R groups that block things from getting in and hydrogen bonding. It's also important to understand that molecular weight has a lot to do with boiling point. So the trend is that the higher the molecular weight, the higher the boiling point. And this is because as you get these bigger molecules that are at higher molecular weights, you get more intermolecular bonding, whatever kind it may be. It may be just van der Waals forces, like for a long hydrocarbon chain, whatever. You get more of that, which then increases the boiling point, right? These things are holding on tighter and tighter as they get bigger and bigger, and therefore do not want to boil off as easy. All right, the last thing I want to mention here is the types of biological reactions that alcohols are involved in. So there's a few pretty key ones I'm going to mention here, but just keep in mind that this is not an exhaustive list, and this is just, I'm kind of cherry picking some examples. So number one, they act as acids and bases, right? The hydrogen attached to the oxygen in this alcohol group is acidic, so it can be lost, it can be gained, therefore it can act as an acid and a base. Another really important function of alcohol groups or hydroxyl groups is that they participate in oxidation reduction reactions, and therefore they can act as electron-carrying molecules. This is especially important in the electron transport chain. So in the electron transport chain, you have a molecule called coenzyme Q, which is an electron carrier. And so it exists as either ubiquinol or ubiquinone. So ubiquinol is the hydroxyl version, whereas ubiquinone contains a ketone group. So go look this molecule up if you don't know what I'm talking about. But just know here that ubiquinone is the oxidized version of coenzyme Q, and ubiquinol is the reduced version. And so which one is the electron carrier? Well, it's easy. You just remember your little friend oil rig. Oxidation is loss of electrons. Okay, so we know that's not the electron carrier. Reduction is gain of electrons. Okay, cool. So we know that what happened was you had the ubiquinone and that gained 2 electrons to become ubiquinol, and now that acts as an electron carrier. And so, of course, that carries these electrons through this electron transport chain, which eventually pumps these hydrogen against their concentration gradient, which then drives the ATP synthase to make ATP for your body, which is an important molecule. So this redox function really kind of applies to a lot of the oxygen-containing functional groups. And so I'm going to go on and I'm going to talk about ketones, aldehydes, carboxylic acids, etc. Just know that this applies to a lot of these different functional groups. The next functional group I want to talk about, or actually this is a family of functional groups, and that is ketones, aldehydes, carboxylic acids, and esters. And they all share one similar characteristic, and that is a carbonyl group. And it's important to note here that you can convert aldehydes and ketones to carboxylic acids using an oxidizing agent, and you can then convert carboxylic acids back down to a ketone or aldehyde using a reducing agent. So you can interconvert between these. You can create esters via Fischer esterification. So these molecules are all kind of related to each other. So let's start with a ketone. So a ketone has a carbonyl group that is surrounded by 2 R groups. So in other words, you have this carbonyl group, and on both sides of the carbonyl carbon, you have two R groups. In contrast, an aldehyde is like a ketone. It has a carbonyl group, but instead of two R groups, it has one R group on one side and a hydrogen on the other side. It's kind of like it is attached to the end of a molecule. That's how I like to think of it. An aldehyde is attached to the end of a molecule. So, it has this double bond to an oxygen, and then because it's the end of a molecule, you just have a hydrogen, whereas a ketone is like in the middle of a molecule. That's kind of how I generally think about it. The next group is called a carboxylic acid. And a carboxylic acid has both a hydroxyl group and a carbonyl group. So it's got that acidic OH and it's got that carbonyl carbon. And lastly, there is an ester. And an ester is synthesized from a carboxylic acid via Fischer esterification. And it contains both a carbonyl group and an OR group. So it's got this oxygen attached to an R group, which is attached to the carbonyl carbon. So it's like a carboxylic acid, only it's got this OR instead of OH. All right, let's start to think about these physical properties. What are going to lead to the different trends we're going to see? Let's mull over this for a second. So think about the carbonyl bond. So this carbonyl bond is a very polar bond, right? You have this oxygen that's double bonded to a carbon, and the oxygen is much more electronegative than the carbon. So it produces this dipole, right? You have this delta negative oxygen and this delta positive carbon, right? You have these partial charges on the different atoms, the carbon and the oxygen. In addition to that, a carboxylic acid has this OH group that can hydrogen bond. So that's also important to remember, right? Hydrogen bonds are important for determining both boiling point and solubility. So those are kind of the things to keep in mind now that we're going to get into the different physical properties of these four different functional groups. All right, so which of these molecules is the only one that can hydrogen bond with itself? That would be a carboxylic acid. So that's going to have the highest boiling point, right? These are going to be hydrogen bonded, holding on to dear life to each other. You're going to have to put in a lot of energy to make a solution of carboxylic acid boil. All right, so carboxylic acid is the highest. What's the next? Well, that's going to be ketone. A ketone is going to have the next highest boiling point, and then an aldehyde is going to have the lowest of these three. Ester, less important to know, just know that that's similar to a ketone and an aldehyde. But for now, know that a carboxylic acid has the highest boiling point, ketone in the middle, aldehyde lowest. And at this point, I hope you're thinking to yourself, wait, why would a ketone have a higher boiling point than an aldehyde? That doesn't make much sense. Well, this is because the ketone has two R groups surrounding this carbonyl. And what that does is these R groups are electron donating groups, right? So this makes the carbonyl bond more polarized. In other words, this delta positive charge on the carbon and this delta minus charge on the oxygen of the carbonyl bond are both going to be a greater magnitude for the ketone. And so what happens then is you have these dipole-dipole interactions where you have carbonyl groups interacting with each other, right? You have these intermolecular forces form between the delta minus oxygen and the delta positive carbon between different molecules, and this contributes to the boiling point. So keep that in mind when you're thinking about why a ketone has a higher boiling point in general than an aldehyde. And as I kind of briefly mentioned there, ketones and aldehydes cannot hydrogen bond, but what they can do is they can do dipole-dipole interactions, right? Because of that highly polarized carbonyl bond. And for the sake of the MCAT, you can tell esters to F off. So let's next talk about the solubility of these different molecules. This is pretty easy. Carboxylic acids are soluble because they can hydrogen bond with water. Ketones and aldehydes are also very soluble within water because they can hydrogen bond with water. And you might be thinking, wait, but they can't hydrogen bond. But when you have water that has this O attached to an H, that oxygen can hydrogen bond. And so you have a ketone or aldehyde that is a hydrogen bond acceptor, and you have a water molecule that is a hydrogen bond donor. So you can form hydrogen bonds if you have water around. Same goes for esters. They're soluble. They can hydrogen bond with water through being a hydrogen bond acceptor. So that's all of those. And again, keep in mind that the limit is about 5 carbons attached. So, take a aldehyde that is 1 carbon chain long. You keep adding these carbons onto the chain, and when you reach 5 carbons, you are right at the limit of solubility, right? That aldehyde is not going to be very soluble at all in water. All right, so that's some of the physical properties of these carbonyl-containing functional groups. Let's talk about the biological function that some of these functional groups serve. So as I talked about before, hydroxyl groups can actually be oxidized into these carbonyl-containing functional groups. It can be oxidized either to an aldehyde or to a carboxylic acid. And so these play, obviously, again, a big role in carrying electrons and being involved in redox reactions. The next functional group I want to talk about are ethers. So an ether is an oxygen surrounded by 2 R groups. So it might be CH3 connected to CH3 connected to oxygen connected to CH3 connected to CH3. It's basically this oxygen in the middle of a hydrocarbon. And if you remember back to the glory days of OChem, you will remember that ethers can be synthesized from alkyl halides and alcohols in a process known as William ether synthesis. And in terms of its physical properties, there's a few different things to understand about an ether. The first is that it cannot hydrogen bond. Obviously, we don't have an oxygen bound to a hydrogen, so no hydrogen bonding to itself. Therefore, the boiling point of ethers are very low. No hydrogen bonding can occur between molecules, and also it's not much of a dipole. So you don't get these dipole-dipole interactions that are seen within ketones and aldehydes. So for instance, dimethyl ether, which is essentially an oxygen surrounded by a methyl group on each side, has a boiling point of negative 23 degrees Celsius. So this is much lower than the boiling points of carboxylic acids, ketones, aldehydes, and even esters. As with the other functional groups, as you add on more and more carbons, and you grow these longer and longer chains on either side of this ether, you get an increase in boiling point. So again, boiling point increases with molecular weight. So that's boiling point. What about solubility? Well, ethers are slightly soluble, and they follow the same pattern that the more carbons equals less soluble. As you get these longer and longer hydrocarbon chains, you get less and less soluble molecules. And these are only slightly soluble because they weakly hydrogen bond with water. And again, these ethers are going to be hydrogen bond acceptors, not donors, since they don't have hydrogens. And I like to imagine these R groups on either side of the ether as blocking molecules from getting in and hydrogen bonding with the ether. Even though this is not quite how it happens, in that way I can kind of remember, okay, ethers are not quite as soluble in water because we have these R groups that get in the way. Therefore, ethers are only slightly soluble in water.
Thanks for checking out the Prospective Doctor MCAT Basics podcast. Sam's doing a killer job taking you through the most important MCAT topics, but what if you need a little extra help? How does a 5, 10, or even 15-point increase in your score sound? Imagine how your chances at admission could increase. Med School Coach's MCAT tutoring can get you there. With the most rigorous selection process of any tutoring company, we see amazing results. We deconstruct each student, find a plan that is going to work, and help execute it. That's why our students add an average 12 points to their score. Completely physician-run and operated, and focusing on nothing but medicine. It's no wonder over 10,000 past students have trusted Med School Coach to get them through the MCAT and into medical school. Check out medschoolcoach.com today and mention code PODCAST for 5% off.
So what biological role do ethers play in the human body? Well, the answer is not that many in terms of the research I did in looking into the biological function they play. One place they do show up is in ether lipids. So these are lipids that have an ether group near the head of the lipid, and they play a role in membrane fusion, according to a 2018 paper. All right, let's switch gears here a little bit and start talking about nitrogen-containing functional groups. All right, so let's get into amines and amides, which are both nitrogen-containing functional groups. Amines are derivatives of ammonia, which is NH3, whereas amides are carboxylic acid derived. Essentially, it is just like a carboxylic acid, but instead of that hydroxyl group, you have an NH2 bound to that carbonyl carbon. So let's first get into amines. So amines, like alcohols, can either be primary, secondary, or tertiary. So a primary amine is a nitrogen attached to one R group and two hydrogens. And keep in mind that this nitrogen has one lone pair of electrons. A secondary amine is a nitrogen attached to two R groups, one hydrogen, and has one lone pair of electrons on that nitrogen. And then lastly, you have a tertiary amine, which is a nitrogen attached to three R groups, again with a lone pair on the nitrogen. And just like alcohols, the classification of amine actually affects the different physical properties of these substances. So again, hydrogen bonding plays a big role in determining these physical properties. What are the atoms that can hydrogen bond? Well, that is an F, an O, or an N that are bound to a hydrogen. So in this case, if we have a primary or a secondary nitrogen, then these can both hydrogen bond, which is great, right? They form these really strong hydrogen bonds. What is important to note here, though, is that nitrogen cannot hydrogen bond to the same extent as an oxygen can. And why is that? Well, the oxygen has two lone pairs of electrons that can both contribute to a hydrogen bond. So in other words, this single oxygen can hydrogen bond to two other molecules. Whereas with a nitrogen, you only have one lone pair of electrons, so you can only form one hydrogen bond. So essentially, an oxygen can hydrogen bond more efficiently than a nitrogen. And so therefore, they form, in a sense, stronger hydrogen bonds. I guess that's probably the best way to think about it. They form stronger hydrogen bonds. So in terms of boiling point then, these amine groups are going to have a lower relative boiling point as compared to a hydroxyl group. And then again, we look through primary, secondary, and tertiary and compare their boiling points and find that the primary amine has the highest boiling point. The secondary amine has the medium boiling point, and then the tertiary has a much, much lower boiling point. And why is that? Well, that's because that tertiary amine cannot hydrogen bond. And again, the secondary amine has this extra R group compared to the primary amine, which can kind of kick out other secondary amines from hydrogen bonding. And therefore, you have kind of less hydrogen bonding because that gets in the way. So that leads to a primary amine having a higher boiling point than a secondary amine. And once I get done presenting all of these different functional groups, I'm going to go back and I'll kind of rank the boiling point of all of these together so you can kind of see where they stand in terms of comparing, say an amine to a ketone. So what about the solubility of amines? Well, they can all hydrogen bond with water, right? Because they have that nitrogen. Of course, for the tertiary amine, it can only act as a hydrogen bond acceptor. And because of this, they're all very soluble. And again, the solubility tends to fall off after about 5 or 6 carbons are bound to that amine group. And the last thing I want to mention here is the physical property of smell. This is really for your interest. This is not going to be on the MCAT, hopefully. But it's interesting to know that as amines get bigger in terms of going from primary, secondary to tertiary, they tend to start to smell fishier. So for instance, trimethylamine, which is a tertiary amine, smells like decaying fish, which is kind of gross. And there's actually a disease that goes along with this smelly molecule called trimethylaminuria. And essentially what happens in trimethylaminuria is the body is unable to break down trimethylamine. And so what happens is that you get a buildup of this trimethylamine and you basically smell like rotting fish, rotting eggs, garbage, or urine. And I don't mean to make light of this disease. I mean, I'm sure people will have it, walk around being kind of self-conscious, or, just put yourself in the shoes of someone who has it. That'd be awful, right? But I think it's kind of an interesting example of amines. All right, so that's amines for you. Let's talk about amides now. So as I said, amides are carboxylic acid derivatives. They are synthesized by reacting an amine group with a carboxylic acid, which produces an amide. And when you're asked to identify these on the MCAT, you're going to look for two main things. That is a carbonyl group, which is a carbon double bound to an oxygen. And then you're looking for that same carbon that's double bound to the oxygen to also be bound with an amine group. The simplest amide is called formamide. So that's just an amide with a single carbon. Then you have acetamide, which is a 2-carbon amide. And then you have propanamide, which is a 3-carbon amide. These are kind of just the common names. But this brings up a really important thing to know for the MCAT, and that is these common prefixes. So that's form, aceta, and propion. And so you can remember form is a single carbon molecule, aceta is a 2-carbon, and then propion, which sounds a bit like propanol, is a 3-carbon. So those are all somewhat easy to remember, but important for the MCAT. So let's talk about amides' physical properties now. So going back to boiling point and solubility, again, what really plays a big role in these? Well, that's hydrogen bonding and also dipole-dipole interactions. And so you look at these amides and you can see, number one, they can hydrogen bond since they have this nitrogen that is connected to a hydrogen, and they can have dipole-dipole interactions because they have these carbonyl bonds. And because they can participate in both these interactions, hydrogen bonds being the stronger of the two, then they have very high boiling points, around 200 to 300 degrees Celsius. And again, the addition of more carbon units increases the boiling point above this already high value. And it is definitely important to mention here that these amides can also be tertiary. In other words, the nitrogen attached to this carbonyl can be attached to 2 R groups. And in this case, that molecule cannot hydrogen bond with itself, right? We don't have a nitrogen attached to a hydrogen, so no hydrogen bonding can occur. So obviously, a molecule that contains a tertiary amide is not going to have the same really high boiling point that, say, a molecule with a secondary or a primary amide group would have. That's important to keep in mind. So since this amide group has this nitrogen that can hydrogen bond, obviously it will be soluble within water. Water will be able to hydrogen bond with it, and therefore molecules containing this amide group are very soluble. All right, so let's briefly talk about the biological functions that amine groups and amide groups play within the body. Other than, of course, amine-containing compounds tend to be really stinky and smelly. Interestingly, many neurotransmitters actually contain amine groups. So that's kind of interesting. And also, amine groups are important for amino acid synthesis. Obviously, amino in amino acids refers to an amine group. And then amine groups are important for acid-base activity. So they can donate a hydrogen, they can pick up a hydrogen, so they play an important role in that. We'll start with amides' biological function with this little riddle. What famous type of bond is actually an amide bond? And I know what you're thinking. No, this does not actually begin with the first name James. What it really is it's a peptide bond. So if you're thinking peptide bond, good for you. You're pretty smart. This is something I really didn't think about till you really go look at an image of a peptide bond on Google or something, and you'll be like, wow, that's actually a amide group. And so that's something you kind of don't really think about. Amide groups are also found in a lot of other structural molecules because they form these really strong bonds. So things like nylon and Kevlar contain these amide functional groups because those bonds are so strong. All right, so that's an introduction to some of the main functional groups that you'll see on the MCAT. What I really, really want you to take away is that a lot of the physical properties of these functional groups or compounds containing these functional groups rely on the fact that these functional groups can either hydrogen bond or they can't hydrogen bond. And the extent to which these functional groups hydrogen bond determines their boiling point and also their solubility. So again, more hydrogen bonding equals higher solubility and a higher boiling point. And before I move on and talk about some less known functional groups, what I want to do is I want to kind of wrap all this together so that you have a picture in your head as to how to compare the boiling points of all these different functional groups. So I'm going to go through and I'm going to tell you what has the highest and what has the lowest and kind of go in numerical order down the list of highest boiling point to lowest. So to start out, the functional group with the highest boiling point is amide. So molecules that contain amides have higher boiling points than all the other groups. And going down the list now, we have first amide, then carboxylic acids, then alcohols, then ketones, then aldehydes, then amines, then ethers, and then hydrocarbons last. So as the mitochondria is the powerhouse of the cell, amides are the powerhouse of the boiling points. And what about solubility? Well, as I kind of went through those, I'm sure you noticed a pattern here. Pretty much all of these functional groups are somewhat soluble. And so you can kind of remember that amides, carboxylic acids, alcohols, ketones, aldehydes, and amine groups are all pretty much soluble within water, right? The two that are not are ethers and hydrocarbons. So those are the ones that are not soluble or at least slightly soluble. And the big thing to remember here is that as you add on about 5 or 6 substituent carbons, you begin to have these compounds that were once soluble containing these functional groups now become insoluble. So for example, you have ethanol, and ethanol is the alcohol that we drink to have fun at parties and stuff. And this is easily soluble within water, right? Remember the story of my friend mixing in water with alcohol after he would drink his parents' alcohol. So easily soluble. But then you start adding on carbons, you get to pentanol or hexanol, and these alcohols are no longer soluble within water. All right, and the very last thing I want to talk about here, and I promise this is the last thing, is the relative reactivity of each of these functional groups. Because I promise you the MCAT loves this shit. And you're going to see this come up probably in 2 different ways on the MCAT. The first is that they may give you a set of molecules or something like that, and you need to order them in terms of their reactivity. And so what you're going to want to do there is just look for the functional groups and say, okay, this has the number 1 most reactive functional group. Okay, this must be number 1, and then blah, 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 and you just sort through down that. And this can get a bit dicey when you're trying to compare molecules with functional group A and then functional group B, and it's like an amine versus an alcohol or something, and you're like, I don't really know how to compare those. So, therefore, I'm going to present the reactivity of different carbonyl-containing species. So, I'll talk about, carboxylic acids, anhydrides, amides, anything that contains a carbonyl I'm going to talk about, and I'm going to rank these for you. All right, so starting with the most reactive carbonyl-containing compound, that is an acyl halide. And so this is a carbonyl where the carbonyl carbon is attached to some halide group. So, chlorine, fluorine, bromine, etc. And the next is an acid anhydride. So this is a anhydride, which is essentially 2 carboxylic acids attached together, and I'll get into that when I talk about the less known functional groups in the next segment. And then we have just a aldehyde, which I talked about earlier. Then we have a ketone, then an ester, which is about as reactive as a carboxylic acid. And then we have an amide, and lastly we have a carboxylate ion, which is just a carboxylic acid that has already donated that hydrogen. So it's a negatively charged carboxylic acid. All right, so that's a brief overview of the reactivity of some of these different functional groups. And I didn't cover these in as great of detail as I did with the physical properties. And that's just because I don't think these are necessarily as important as knowing the different physical properties. I think reactivity really is more important when we're talking about elimination, substitution reactions, and some other of those organic chemistry reactions, not necessarily in just memorizing, this functional group is this functional group is greater than that in reactivity, etc. So In my opinion, if you want a more high yield look at reactivity for the MCAT, go look at the organic chemistry reactivity in terms of substitution and elimination reactions. All right, in this next segment, I want to go over some of the less known functional groups. And all I'm going to do is I'm going to name these off, describe their structure, and I'm skipping the physical properties in reactivity just because I don't think it's as important to know for the MCAT. And one thing you can do if you really want to follow along is you can go Google these molecules as I talk about them, so that way you're putting a face to a name. I'm sure you've had friends that will describe their date's face for you and say, they looked like this, and you start to put together this image inside your brain, and you're like, okay, I know exactly what you're talking about. I know what they look like. They look like a 22-year-old Megan Fox. And then you finally get to meet your friend's date, who is now their girlfriend, and you say, hey, nice to meet you. You look more like a bald Britney Spears than I thought. And so obviously sometimes you picture something in your head and it looks a totally different way. So all I'm trying to say is hopefully you picture these molecules right. If not, go Google them and follow along with me. The first functional group to know is an anhydride. So an anhydride is essentially two carboxylic acids attached together. So you have two carbonyl groups, and in between these carbonyl groups, you have an oxygen. And there can be R groups attached to either end of this anhydride. The next functional group to know, less common of course, is a hemiacetal and a hemiketal. And these form when you react a ketone or an aldehyde with an alcohol. And essentially what you end up with is a carbon attached to four different things. So it's going to be attached to a hydroxyl group, and that comes from the carbonyl oxygen. And it's also going to be attached to this OR group, which comes from that alcohol that reacted with the carbonyl. And then depending on whether you had a ketone or an aldehyde to start, you're either going to have two more R groups or an R group and a hydrogen connected to that carbon. The next group is called an amine, and this is pretty easily recognized. It is a nitrogen that has a double bond to a carbon. So it looks like a lot like a carbonyl group, but instead of that oxygen that's doubly bound to carbon, it's a nitrogen. So that's an amine. The next is a Thyle group, which is just a sulfur attached to a hydrogen. I like to think of this like a hydroxyl, except you have a sulfur. So that is an SH, Thyle group. And then you can have a phenol group. And this is a phenol ring attached to some R group. So what is a phenol ring? Well, that's a benzene ring, which is this six-membered carbon ring that is aromatic. And finally, the last one I want to mention is called a nitrile group. And this can be recognized easily because it is a nitrogen with a triple bond to carbon. And you might be thinking, wait, isn't that the same thing as cyanide, right? C triple bond N minus? You're right, but you're wrong. So a nitrile is an organic molecule that contains this C triple bond N, whereas cyanides are inorganic molecules that contain a C triple bond N with a minus charge on that carbon. All right, that concludes this podcast on functional groups. Thanks for listening to Prospective Doctors MCAT Basics with your host, Sam Smith. As always, I appreciate you listening. If you like this podcast, go ahead and rate us or review us on iTunes. Helps with the rankings, helps get this to more people. Stick around for a recurring segment called Indecent Information. If not, I hope you listen to the next podcast. Thanks again. All right, so now on to a segment called Indecent Information. So I'm going to talk about real briefly is why does alcohol make us lose inhibition, do stupid shit, dance on tables, whatever it may be? What is it in our brains that alcohol changes? So if you think back to psychology, you will remember that alcohol is a depressant. In other words, it decreases brain activity. So the underlying mechanisms then of alcohol's effect on your brain and on you must be in terms of decreasing brain activity. So how does that happen? Well, alcohol has been shown to interfere with several different neurotransmitter systems in the brain, and it acts in two main ways. That is to increase the inhibitory neurotransmitters and to decrease the excitatory neurotransmitters. So I'm going to talk about each of these. So number one, as I said, alcohol increases the inhibitory neurotransmitters. So alcohol has been shown to increase GABA receptor function. And if you remember, GABA is gamma aminobutyric acid, which is a neurotransmitter, an inhibitory one in this case. And so alcohol then is shown to increase the receptor function, therefore acting to decrease brain activity. So that's one way it does it. The other pathway that's been studied is in terms of the glycine neurotransmitter. So glycine is known to be another inhibitory neurotransmitter, and alcohol has been shown to increase the binding of glycine to its receptor. In other words, alcohol is the wingman for glycine. Alcohol goes up to this glycine receptor and he's like, hey, what's up? What's good? How we doing? This is my friend Glycine. He's really cool. He's a nice guy. You guys should really meet each other. You guys should talk. And then boom, they're together. So alcohol essentially promotes this binding. All right, so that's the first way that alcohol influences the brain. The second way that alcohol influences the brain is that it decreases excitatory neurotransmission. So there are a few major excitatory neurotransmitters within the brain. A few of those are amino acids such as aspartate and glutamate. And both of these neurotransmitters act through binding the NMDA receptors. And what happens in short-term alcohol exposure is that the NMDA receptors seem to be inhibited. And so by inhibiting these receptors, you actually decrease the excitatory neurotransmission within the brain and therefore continue the depressant or inhibitory effects of alcohol on the brain. And so it's a combination of both increasing inhibitory neurotransmission and decreasing excitatory neurotransmission, and probably some other effects that I'm not talking about here that tend to, loosen inhibitions, make you really sleepy when you drink, etc. A lot of those effects you feel from alcohol.
Thanks for listening to Prospective Doctor's MCAT podcast. If you're a pre-med, you'll want to check out prospectivedoctor.com for tons of free tools, articles, and more podcasts that cover your pre-med life. And if you need help on the MCAT or getting into med school, check out medschoolcoach.com for the experts.